let's get started. Today's Qualia structure member interview, and that sound was the winner of the sound contest this year. Okay. All right, so today we want to interview Steve. Steve is a member of the Qualia structure, and he's very knowledgeable and experienced in the category theory, and forms a very significant part of our project. And today I want to ask Steve's past and current and future research interest, and also in the course, maybe we can ask various things. And particularly, two of the research in the past is probably interesting for us. One is a developmental angle, and also another one is a recursion, respectively central interest for Yusuke and also Makiko, but also in general, other stuff as well. So yeah, Steve, please go ahead.
Okay, thanks, Now.
Yeah.
Yeah, I've been working in the category theory approach to cognitive science for about 12 years now. Originally with Graham Halford, who's a psychologist at the University of Queensland, and then with Bill Wilson. Originally, we were working on the sort of relational complexity approach to development and cognition. The idea that the basic idea is how the difficulty of particular cognitive tasks depends on the relationship, the complexity of the relations that are involved in that task. And a lot of this work is outlined in our Behavioral Brain Sciences target article in 1998, where we discuss these ideas. And we've been working on this for quite a while. Some of the classic tasks, for example, transitive inference, and how the ability to do transitive inference changes throughout the life. Particularly around the critical point is around the age of 5. And the original experimental work was done by Graham Halford and colleagues, and in particular Glenda Andrews, who had done a lot of experiments on this sort of thing. And not just transitive inference, but the whole range of developmental experiments on children, looking at how different tasks seem to have a very common aspect of difficulty, and from all these different tasks, we formulated this notion of relational complexity. The basic idea is that children around the age of 5 seem to go through this transitionary period where they can process, say, binary relations, but not ternary relations. That is an interaction between 2 variables versus 3 variables. And this is the basic idea behind relational complexity theory. And so we've been working on this for a long time. Probably the most recent exposition of this is in the book by Graham, Bill, Glenda, and myself, published by MIT, called Categorizing Cognition. And that gives a sort of a nice overview of the whole concept. The idea that as we develop this increasing ability to process more complex relationships between the task variables. Now, in conjunction with that, I got interested.
Maybe I have a question up until here. So, in a sense, where was your sort of the original motivation of getting involved in this, relational complexity theory? Were you originally interested in the development, or more of the theory side, or cognition side, or how did this came about?
It was a bit by chance and a bit coincidentally, actually. Mm-hmm. So my original training was in computer science, and so I'd done quite a lot of work in relational database theory
Yeah, that's what
during my undergraduate and postgraduate studies at the University of Queensland in the computer science department. And it was just by coincidence, actually, Graham gave a talk outlining the basic ideas behind this notion of relational complexity in cognition and cognitive development, and it was very natural connection between what he was talking about and what I'd already had done in the computer science side of things.
I see.
So after I finished my PhD, I was originally working in neural networks approach to cognition. And after I finished my PhD, I went to work with Graham. Graham invited me to work together on these ideas, and then that led to it was just a natural fit of the theory and on the computational side and the psychological side. So that's where it started.
I see.
In 1995.
I see. But so the Graham and so Bill had this, pretty much the first study of the category theory application of that one was just a sort of sketch or idea, right? Probably.
Yeah. So their original paper, 1980, was, as far as I know, the very first paper to apply category theory to empirical psychology. I mean, some people had the sort of the general conception of using category theory in psychology before them, but they were the first to actually apply it to psychological data. The notion of structure. The key point there was the notion of how different tasks have different sort of levels of structure, and since the category theory is a sort of a mathematical formalism of structure, at the time it was seemed to be a nice way to approach it. And so, however, having done that, we sort of shifted towards the relational approach, and the category theory side of it was sort of left in the background. And then I got interested in category theory for other reasons. But then my interest in category theory is more to do with the notion of structure in cognitive science is somewhat vague and informal. Many people talk about structure, but they use it in different ways and not always consistently. And probably my interest actually in my PhD was on the systematicity problem that was raised by Fodor and Polishin. And the notion there of the idea that human cognition has sort of these commonalities, the sort of cognitive capacities that we have are not arbitrary, but sort of are organized around these structurally related groups. And that problem had been ongoing for a long, long time, and I sort of addressed it I had looked at it from the connection neural network point of view. The irony there was that both the people, the point of systematicity was supposed to be an argument. It was a property of cognition that was supposed to argue in favor for a sort of a classical or a simple system approach to the notion of cognitive architecture. And the idea was that only simple systems could capture this notion of structure that was evident in the way that people do things. But and then on the other hand, neural network people said, oh, well, no, neural networks can also capture this notion of structure. And so there are really two different views of structure. And so I wanted to get to the bottom of this from more of a computational perspective. And it soon became clear that even in computer science, there were different ways of treating structure. And so that got me interested in the more formal approach, and it got me interested in category theory. And then while I was learning about category theory, then I went back to, I did two things more or less at the same time. One is review the systematicity problem from a category theory perspective, and also review our relational complexity approach to cognitive complexity from a category theory perspective. And then in 2009, myself, Graham, and Bill redid the relational complexity approach from a category theory perspective. And then the year after that, Bill and I looked at the systematicity problem.
Yeah.
Also from a category theory perspective.
Yeah. Maybe at this stage, I also want to ask another question, because as you know, our project is called Qualia structure, right? And in fact, we have been using this, one particular kind of book written for the general public, which is sort of introduction to the structuralism by some sociologist in Japan, who's actually extremely knowledgeable across many different kind of domains. And but this book explained the sort of introduction to structuralism by looking at the history of the mathematics, and pointing out that things that Levi Strauss was probably inspired by mathematics of the modern mathematics, which tried to kind of extract the structure through the the transformation and so on, the group theory, and then he applied it to this I don't know what's called anthropology kind of data or enigma, and then also went to the mythology and so on, right? And we thought that this book is extremely clear and also interesting and so on. But at the same time, the conclusion of the book was that this notion of the structure or the formalism is, in a sense, really left to Levi Strauss' ingenuity himself, and it's very difficult to replicate or systematize, the kind of analysis that they did. So, if we were to talk about or Qualia structure as a sort of extension of structuralism, we definitely need some more extended or modernized version of the analysis, which is, I think, the category theory. And the reason why, your and also Hayato's contribution has been quite, important. But do you have any kind of a statement or, especially when you are starting to look at the structure in relation to the structuralism kind of approach, did you have any kind of discussion or idea in relation to category theory?
I just see category theory as more of a landmark, a way to relate, sort of like a way to relate different people's ideas to something that's common in a sense. The reason why I struggled with cognitive science, particularly the connections approach to cognitive science, is that everyone talks about structure, but they always talk about it in a different way. And category theory gives you sort of a sense of like a universal language for talking about structure. It's a kind of, so that it's not that you necessarily have to say that that what you're talking about, it has to be A or B, but it gives you a landmark to relate how A or B can be relatable. You often find in psychology and cognitive science that the debates never seem to settle on, never seem to resolve very much, but because they seem to talk in a way that's in two different languages that are not really compatible,
right? Or
that there's no common frame of reference.
Right.
And category theory often provides this common frame of reference. That it's not that a particular category theory structure or concept is necessarily the right way to do it. That's not so much the point. As it gives you a way to relate two different perspectives that was missing, I think, in a lot of particularly in the systematicity debate. The debates just went round and round in circles for a long time. I felt, particularly because there was no common ground for relating each person's perspective. I think category theory provides this very nice, formal, very precise way of doing this.
Yeah.
So I suppose that the other way to look at it is that, in some sense, category theory is quite natural perspective for a lot of what cognitive scientists view cognition as a kind of a relational process. It's not just from our perspective, not just from the relational complexity theory, but a lot of other, particularly analogy researchers, they view the capacity to process relationships as more fundamental, as just as important as the elements themselves. And so category theory is a very natural perspective, very natural formal perspective on this view. And so in that sense, I think the notion of structuralism, when you say structuralism, I'm not exactly sure what's meant there, but
yeah, so that's the sort of the problem we have been kind of finding, right? Like I've been as you were there in the consciousness talks this week, many of the language or concepts we are talking about feels like it's the same thing, but if we leave that in discussion or writing to psychologists and also philosophers and so on, then many things becomes really unclear and ambiguous, and depending on the context, things can mean X and Y, and it's going along, right? So the paper that Yusuke and Hayato and I were discussing so far mainly talk about the Piaget development and his sort of the ideal goal of the mathematizing this cognitive development, but Yusuke knows more, but his description has been quite confusing and inconsistent even with himself, right? Yeah.
So once I started learning the category theory, it helped me, as I was saying before, for me it provides more of a frame of reference. So when people have these ideas, it's often hard for me to understand exactly what someone is saying until I can feel I can translate it into some sort of category theory construction. Then I have some idea about how to relate to someone else's perspective.
Yeah.
In that sense, I find it like a landmark or a frame of reference to sort of orient my thinking about other people's thinking. That's why I find it quite useful just in that perspective.
I don't know. Do you guys, for example, Masafumi, you are more from the sort of mathematical or physics kind of side of the people. So when you read the papers from psychology or consciousness research, do you often get this kind of frustration or confusion, like whether the definition or concepts are unclear or confusing?
Yeah, I think so.
Yeah, but when that happens, you just go through and then skip, or trying to mathematize in your house?
Yeah, I do not mathematics. Just I need to read as many papers as I can. Then probably we need to extract some common, common space among the many researchers.
Yeah, probably that's the natural attitude, I guess. Yusuke, do you have anything to say so far?
Yeah, thanks, Steve. So, as now Jason said, Piaget conceptualized structure from the group theory. So do you think do you have something about his theory? So you can say something from the category theory. Actually, we are now discussing about how we can conceptualize Piaget's theory in terms of the category theory. But do you have something to say about this?
Well, I mean, you can just think of, I guess the immediate point would be, you can think of category theory as just a further generalization of group theory. And that would be one route.
Right.
But I think, category theory is a whole lot more than that. And one of the interesting things for me is the relationship between the sort of algebra, starting from your group theory perspective, from the algebraic view of cognition versus the non-algebraic or the spatial. In a sense, this is the symbolic you could view the symbolic sub-symbolic debate as an aspect of this. And so if you think of language as being algebraic and vision or perception being spatial, then it's natural to look at category theory as a way of bringing those two different aspects together. I mean, certainly at some point, a theory has to integrate both the spatial and non-spatial aspect, or the algebraic aspects of cognition, and category theory would be a nice way to do that, because it's already been done in mathematics, linking, say, algebra and topology or algebra and geometry. So
in fact, this is exactly what we were talking, right, with Hayato and Yusuke this week. And also, if as you know, pretty much, I've never attended in a conference which deals with both language and symbols and so on one hand, and also, space or, vision in a coherent and unique, unified manner. Typically, it's completely separate session, and they don't really talk to each other. I mean, there is no way to understand it, right? So I'm really quite, novice to this language side of the things, and I've been just, starting to read linguistic and cognitive linguistic, and the distance from this, vision science is so far that it's pretty difficult to, deal with. And maybe, one reason why we may be thinking that maybe we are coming to close contact is that, as Masami is doing, deep learning, and also, word-to-back, or, other stuff like BART, that tries to sort of vectorize or, parameterize language and the connections in a way that, we use a graph theory kind of idea. But when we go into that direction, then it starts to become also difficult to connect back into the spatial kind of stuff as well for the, vision stuff. So, I think I also agree that algebraic and also, spatial kind of orthogonal axis, almost orthogonal into one thing, like what you're doing in currently, like a sheaf theory, like space of the topology, and then within that topology to build up sort of symbolic or sort of algebraic kind of operation. That makes a lot of sense to understand the consciousness as a whole. All right, so that's pretty good so far. And then maybe also to get started talking about the recursion side, which is some of the Makiko's interest. So Hayato joined.
Can I ask one question? Here for me it's kind of too difficult to understand what you are talking about, because it's basically that the discussion is kind of really abstract. So I particularly, for example, want to know like what relational complexity is in development and cognition, for example. Can you more kind of concretely explain what this is, or how the category theory is utilized for understanding the relational complexity, for example?
So just think of a relation as from a mathematical perspective, as just as a subset of a Cartesian product. So a binary relation is just a subset of the product of two sets. It's just a set of pairs, and a ternary relation is a set of triples. And in the example of, let's say the idea is that you can, if a task only requires the most binary relations, say John is taller than Mary, taller than relations is a binary relation, then the younger children can process that kind of task. But a ternary relation, say like John gave Mary a book where there are three, you can think of each of the arguments as like instances of a particular variable, like a relationship between three variables, say the agent, patient, and the object. The ternary relation, and then the idea, particularly in the transitive inference case, is that the younger children have difficulty processing tasks which require ternary relations.
I see.
That's just the basic idea. One of the things that we did in the one of the things that was curious for me, the notion of relational complexity is also important. Well, not per se, but in relational database theory, you have what's called normalizing the database. And so you can, for example, you can have, you know, a relation can have any. You can, you know, in general, usually we talk about binary relations, but you can talk about n-ary relations just as a relationship between n variables. And one of the things that they want to do in relational database theory is to take a database and break it down into its smallest parts, normalize it. The reason for doing that is for data integrity. And say, for example, you have a ternary relation. Now, in some instances, you can break that down into two binary relations and recover all the information from the ternary relation. So it's not it's a kind of normalization process. And this also, the reason why it's not so straightforward in a sort of experimental setting is that in some situations, a person could break the ternary relation into a couple of binary relations to get around this complexity limit. But in some situations, you need to maintain that ternary relation, like in the transitive inference case. So the example of transitive inference is a situation where you have, say, John is taller than Mary, Mary is taller than Tom, therefore John is also taller than Tom. And the idea is that when you give children these kinds of tasks, the step at which they have to link the two relations to form this ordered triple, and from there infer the two endpoints is quite difficult for the younger children, but it seems to be doable at around age 5. However, having said that, there are two general versions of transitive inference, and in fact, it's a topic that I'm interested in revisiting again at this moment. Originally, Piaget thought that transitive inference was sort of the ability to do transitive inference was sort of like a hallmark of higher level cognition, of ability to do reasoning. I think in his original studies, he said it was around the age of 8 or so. And then there was a famous paper, Wright and Trabrasso, published in Nature, I think, which seemed to show that even very young children could do it. But there are certain strategies you can use to get around the difficulty. And so when you correct for these strategies, then it seems fairly consistent that it can't be done until about the age of 5. You know, at sort of the average sort of nominal age. However, after that, sort of comparative psychologists ran their own version of transitive inference, which was done by so-called reinforcement learning. And they found that lots of other species also seem to be able to do transitive inference. But there's a difficulty there, or the difference there. And this is another example of about the debates in psychology, how they never seem to get resolved, is because if you look at the literature, you seem to have these two groups: the animal psychologists who have shown or claim to have shown transitive inference in, say, monkeys, pigeons, crows, even fish, for example. But the way that they do it is by reinforcement learning. So the premises like A and B and B and C are learned by reinforcing the selected choice. So you give them two options, A and B. Let's say they have two cues, say square and triangle. And if they select triangle, you reward it. If they select square, you don't. And through that reinforcement procedure, they learn the preference of, say, triangle over square. And then you give another two, like triangle and, say, circle, and you do the same thing. So you preferentially reward circle. And then you give them the test cue pair, which is square and circle. So the idea is if they preferentially select circle on the first trial, then it's indicative of a form of transitive inference. And so it's somewhat counter Piaget's view. And lots of studies have been published in high-profile journals like Nature and Science, showing that other species, crows and fish and so forth, can do this. And perhaps I think bees, perhaps I'm not sure it's been done with bees, but anyhow. And the idea was, well, maybe it's unclear what to get from these kinds of results. On the one hand, it sort of contradicts the Piagetian view that transitive inference is a sort of hallmark of high-level reasoning when other species seem to have this capacity. But it's a bit strange. Are we claiming then that these other species have a similar sort of cognitive abilities as humans? Well, it would be rather, it's somewhat counterintuitive, and I presume that's why these kinds of studies often get published in very high-profile journals. But if you look at the way that it's done, in the kinds of studies that Graham and his colleagues, Graham, Glenda, and others have do it, the premises vary on a trial-by-trial basis. So, for example, whereas in the animal studies, they only ever do one kind of inference. It's only one kind of relation that they learn by reinforcement. So the learning procedure is quite radically different. Whereas in the humans, they can do it in trial by trial. So for example, in the human case, by contrast, is that you show them, for example, blocks, the 2 block towers, for example, you show them a red square sitting on top of a blue square, and then you show them a blue square, sorry, a red square sitting on top of a blue square, and then you show them another block where a blue square is sitting on top of a yellow square, and then you give them you've got A above B, and sorry, a red above blue, blue above yellow, and then you've got to infer that red should be above yellow. Now, the younger children, 4-year-olds, typically fail at doing this, even though they can understand the 2 premises, whereas the older children can. But the key point about this is that the premises themselves are only ever shown once. The whole set of premises is shown only once. It's not a reinforcement procedure, and so their ability to do this is quite dynamic. Whereas in the other species, it's not dynamic. It takes lots and lots of reinforcement learning to get to, even though they do one-shot generalization to the inference, it takes lots of training just to get them to learn the premises. So some people, and so you get this curious thing where there's really 2 groups. The so-called the studies with the animals is sometimes called implicit transitive inference. The studies with the older humans, it's called the explicit transitive inference. But it sort of begs the question: is what's going on here? Is it really the same process being accessed here, or is it something completely different? And of course, this has implications for the comparative, and this is what sort of the point, and hence the subtitle of our BBS article. It has implications for both comparative and developmental psychology, and also cognitive psychology. What's going on here is, are these 2 forms of transient inference really saying anything about the nature of human cognition versus non-human cognition? And it's kind of a critical question for cognitive science, because we have all these multiple stories, but no way to connect it. And this is another reason why I got into category theory, is because a lot of cognitive sciences and psychology, experimental sort of cognitive psychology, there's not much more than data fitting. So there's more to science than just fitting data. You've got to be able to connect the different aspects. And so we have a rather fragmented field, despite cognitive science being set up as a sort of umbrella term to unify all these different fields on this common quest to understanding mind. And category theory is somewhat analogous. Category theory was set up as a way of linking different aspects of mathematics, where mathematicians realized that they had all these different theories, but there was some sort of commonality between the 2 of them. Well, the same sort of thing applies to cognition. It's one thing to say that we have all these different capacities, but how do they link together? A story to explain that is also needed.
Maybe just to kind of wrap up. So in answer to Masafumi's original question about relational complexity, I guess your explanation was clear, right? right?
Yeah, I roughly understand it. Yeah.
Yeah. And basically, that can potentially explain the how this cognitive developmental ability is explained by this concept, right? And yeah, now that Hayato is here, Hayato and also I and Yusuke was discussing about this relational complexity in infants actually. So which is that the very old children, like Masami, actually your child is below 5 right now, right?
Yeah, 4 years old.
Yeah, you can test it. Test with A larger than B and B larger than B, and then ask A larger than B.
Yeah,
Right.
I'll do.
Yeah, probably she can't do that. Anyway, so then, so children can do only 2 relations. And then, after that, after 5, we can do 3 things. And then it seems like it's really curious that you wrote in the paper that people usually can infer or understand 4 relationships, right? And also, when you show the bar graph or something like that, and then people can kind of grasp and understand up to interactions of the 4 factors.
Yeah.
These are actually quite curious. And when I actually met with a guy in Melbourne this week who knows you, people can probably understand the subject and the object, and then another things, plus perspective or context or something like that. That is a sort of the 4th viewpoint. And then above that, we can't possibly understand, or we don't need it.
Yeah.
Is it true, first of all, that people who can understand a 5th component doesn't exist even in adults?
Yeah, so Graham has a paper in, I think it's Psychological Science. He and his colleagues did this kind of study, and yeah, it drops off after about 4. Even 4 is quite demanding.
Yeah, that
yeah,
I can imagine.
5 is most.
Yeah, people
because of working. I'm sorry. So because of working memory capacity or something. So that.
Yeah, it's related to. Yeah, this is a critical issue. So, and this gets back to the difference between implicit and explicit transitive inference. So, in the book, in various places, we talk about the ability to bind, dynamic binding. So, yeah, the working memory is crucial here. It's not the long-term memory. So in the implicit transitive inference case with the animals, it's kind of a long-term memory because they have to use reinforcement learning to learn the premises, and you only ever see them. The studies only ever show them to do it on one particular instance, whereas in the older children, it's dynamic, so on a trial-by-trial basis. For example, as I mentioned before, in one trial it might be a red block over a yellow block and a green block over, and so on. And then in the next trial, I'll change the blocks entirely. And so, yeah, it's working memory and the ability to make these links dynamically, and make and break these links dynamically. And this kind of task, where this is also a characteristic difference between these sort of structural related tasks in the humans versus the non-humans, is that the structure. So another paradigm is called a relational schema induction paradigm, which we've discussed quite a bit. And the idea is that the individual elements are not so crucial, but the relationships between the elements is crucial. And the element, and this is why the relational approaches to cognition is so important, is because it's not the fact that it's the color red sitting over the color blue, for example. It's the above relationship that's crucial. So to answer your question, it's an aspect of of working memory capacity.
Okay.
Yeah, and then I think it relates to like mentalizing ability. Like so children start with the first person perspective, then second order, and then we can get to the more higher order perspective. And then this, I think working memory and mentalizing ability is also related. And in those ways, I think recursion is very important factor. Yeah, maybe you will give a talk later though.
Yeah, so in the mentalizing, in the BBS paper, various places we discussed about theory of mind, and I think Graham and Glenda have done studies on this kind of thing, where you ask children to view the situation from their perspective, view it from a second person's perspective, and so forth. And then as the number of perspectives changes, the ability to do this kind of task becomes harder. So yeah, it's also related, in a sense, yeah, it's related to recursion too. But there is recursion has another aspect to it, which I may or may not talk about, but yes. So in the
yeah, we can talk about move on to recursion as well. Yeah.
But before going that I now understand the idea of relational complexity, but I'm not still sure how the category theory is utilized for the relational complexity. Is it used for quantifying the difficulty of relational inference, or is it utilized for understanding how humans get to be able to understand the relational complexity?
In the first regard, we would just look. One of the motivations for category theory was there was a particular in the relational complexity view. There was a whole series of tasks that Graham had done, and we wanted to sort of provide a unifying framework for saying why some of these tasks are more difficult. The commonality was that around age 5, there was a whole suite of tasks that the older children could do that the younger children couldn't. In fact, this is the topic of Glenda's PhD thesis, and she had done a lot of this experimental work, not just transitive inference, but another one was class inclusion, another type of problem. One of the motivations for trying this was that class inclusion problem had a bit of a difficulty. We had a bit of a difficulty with it, and so it was a little bit difficult to relate it to the rest of the framework, and so a motivation then was to use category theory to relate the two, transitive inference and class inclusion, as how the two related, and the idea was that transitive inference was the basic idea was that the relational complexity maps onto what's called a product arity, like a binary product or a ternary product, or it's what's called a constrained product or pullback. And so transitive inference is just naturally a particular kind of constrained product. You take take A and B and B and C, and you bind them together on the common element B. This is just called in relational database theory, this is called an equi-join, and it's just a special case of a pullback in category theory. Now, the class inclusion structure didn't seem to fit that, and so after playing around with it for a while, then it occurred to me that, well, if you look at the dual concept of product in category theory, which is a code product, class inclusion came out quite nicely that way. So the motivation there was similar to what I was saying before, in that we had these two different tasks and they didn't seem to relate, but the category theory showed how they could be related in terms of, so one was dual, in a sense of dual construction, but the arity was the same. So it was the way that we formulated it was the arity, i.e. the number of interactions both from the product side and this dual code product side was the same. So that was our motivation for doing that. And then, you can do a lot more for that. So, for example, the question is why. It's not just that the relational complexity theory is more like a categorization of different tasks in terms of their difficulties.
Yeah.
And it's not just that you want. Well, that's one thing. You want to also explain why there is this progression. And so I'm also interested in category theory too. Once you put two things in the common framework, then you have a potential for a path between the two, and therefore a potential for explaining how you go from one system to the other system. And then category theory has a whole bunch of ways of doing this. And in particular, it's not just that you have these constructions, but how these constructions themselves are created. And this led to the notion of the so-called universal construction approach too. So most people, like it's particularly in the symbolic approach to cognitive science, assume that some sort of product construction, but the product itself is is just one aspect of a more fundamental construction, i.e. the universal construction. And so you get an explanation as to why you have products in the first place. And that I found quite fascinating. It provides a more fundamental perspective, I think, rather than just assuming or considering, that, okay, children are limited to binary, young children are limited to binary, older children ternary, and so forth. Well, the category theory approach shows you how to unify this and gives you a more fundamental construction that suggests how that you transcend these constructions.
Yeah, maybe potentially this is kind of the direction that we might want to go in this Gakujutsu Henkaku A. But in B, we emphasize the Yone dilemma kind of approach to Qualia, right? But this, what Steve said right now, this universal construction, this is still like something I have to absorb and completely understand. But the concept called adjunction, which is highly related to this, I think this could be potentially a central theme for the next iteration, which is that there may be a lots of ways that consciousness or Qualia can exist, right? In many versions. But for some reason, we are experiencing this, but not the other. That's, in IIT terms, it's called exclusion. But, this question of why this is not still like, directly addressable. And this adjunction or universal construction, or what Steve is talking about as a systematicity, is in a way, among all possible way to structure things, why we are experiencing, why we are having this in this particular way is potentially something that we can address through this approach. And I think, this would be probably highly unique to the category theoretic kind of perspective.
I see, yeah.
Maybe we need to, I first need to digest this concept, but also, we need to talk about it in the future. Yeah.
But I think that,
can I say? So it means that, relational complexity is sort of very universal phenomena among different animals like humans or other animals. If the sort of learning rule is kind of same, then the, difficulty is sort of similar among the different animals. Something like that. Is that
something like that. There's something sort of fundamental. The notion of if you look at the relation itself is built on a product, or it's a subset of a product, and the product, from a category theory perspective, is probably one of the most basic. Is probably the most basic construction that you can have, where you have more than two things that have to be combined in some way. So, in some sense, it's quite fundamental. And I think the difference is that products you see products in many different sort of theoretical or formal constructions, but they all have this common aspect to them, which is what category theory captures, so that you can think of them as all different versions of something somewhat fundamental.
Okay.
All right.
Yeah.
So far, I and also Hayato joined afterwards. Do you guys have any questions so far to Steve or comments?
I have one comment, a very simple one. It's very easy to understand. The thing which is very easy to understand is category theory capture the basic structure of this kind of relational complexity because of the existence of the notion of the composition of arrow is nothing but the generalized kind of transitivity. The difference between the dialectic graph, digraph, and the category is the existence of transitivity, or that is in formal theory, it is called composition of arrows. So I think that it is, as a Piaget, I think it is a hallmark of our recognition because we directly experience the relation between two things, but also we can think of its composition. So indirect relationships. Without this kind of appearance of indirectness, we don't have the systematic structure of cognition, and this is how to say, very in harmony with the formal setting of category theory, that is the composition of arrow. And I'm not sure, but maybe it is possible that the four-term relation is related to the notion of diagram, like associativity of the composition or something is related to that kind of four-term relationships. So I don't know why, but I suspect that why category theory is so in harmony with our basic cognition is my hypothesis is the category theory began as some kind of meta mathematics, like topology, geometry, algebra, the bridging these things. The mathematics itself is deeply related to the bare core of our cognition, and to bridge these different areas of mathematics, we need to dig into the very primitive structure of our recognition. And then Ehrenberg and McLean find that the notion of arrow, the two-term relationships, and the notion of the composition three-term relationship, and the diagram, like a four-term or that kind of, that's all we need. This is Ehrenberg and McLean's finding, I think. They're very deep finding, not only for mathematics, but also the research on humanities, I think. So this is a very easy comment, and of course it is coherent with Steve's view, I think.
Yeah, good. That was, I guess, a comment rather than a question, right?
Yeah.
Yeah.
Comment.
I think probably, I guess, Steve would just agree, or
it's nice comment because the transitivity aspect, I mean, transitivity is sort of built into the concept of a category. If you have two arrows that are end to end, then you must have the third arrow. It's a nice coincidence because I'm just writing about this at this point right now in terms of explaining transitive inference. It's sort of the kind of irony is that there are these many studies that identify different species being able to do so-called transitive inference, but no one asks why is it so prevalent throughout the animal, apparently so prevalent throughout the animal kingdom, and I think there's just a very simple explanation for this. Which is the point I'm writing about. That category theory provides is very closely related to what Haito just said. If you have two arrows and they're end to end, then you must have the third arrow, which is, in a sense, that a rule for being a category is an example of transitivity.
Okay. So then maybe shall we move on to the recursion? component. So yeah, Steve, you started to talk about the recursion, but maybe can you talk about a bit about your work on recursion or your view about the recursion?
Yeah, this is another example of where category theory, one of the things that category theory gives for free in a sense is this concept of duality. But most people know about recursion, but not many people know about co-recursion. And so whenever you have a concept in category theory, it's often nice to have a look at its dual. So for example, before we're talking about product, and so the dual of product is co-product. So for example, the product of two sets is the Cartesian product is a product of two sets. The disjoint union is the co-product. So it's often fun to see what the dual conception is useful for. And in the case of recursion, category theory provides a sort of a formal way to do recursion. You can also, once you understand that concept, you can turn the arrows around and look at its dual concept, and that's the co-recursion. Co-recursion is often used for processing of streams, i.e. infinite lists. And one of the things that pops out of using the co-recursive approach is maybe such a
Steve. So just quickly, so usually, so the recursion that probably also Michael is interested is like something that goes into increasing in a sense, like let's say if we have a natural number on 3, and then if we recursively increase it 3, 4, 5, 6, blah blah blah, that's what you're thinking as a sort of recursion. And then core recursion is a sort of the reduction into sort of the core or the terminal object or something like that. Like, if any kind of natural number, if you reduce by 1, it ends up in coming back to 1 or something like that.
Yeah, so if in the category theory language, it's called a catamorphism versus an anamorphism, and it comes from Greek, where kata means to tear down and ana means to build up. So the early papers on the category theory approach to recursion in computer science, recursion, co-recursion, make use of this as a way of conceptualizing what's going on. And the idea in the recursive approach, the difficulty is from a cognitive science perspective, you usually have to build up the entire data structure first, right, before you can actually do anything. So that's, in some sense, I mean, it's just a theory. So you may have some way of transforming that into a model where you don't have to do that. But in general, it's somewhat unnatural because, for example, to process a list recursively, you'd have to build up the entire structure first and then break it down step by step. Whereas if you turn the arrows around and look at it co-recursively, you can just process each individual item and then build up the rest of the data structure as you need it. And so it seems to me a more natural way to think about cognitive processing as a sort of stream process, i.e. as a co-recursive process where you're not having to build up these massive data structures in memory. While it's natural to do that in a computer system, it's somewhat unnatural to think about that in a cognitive system. So co-recursion seems.
It's already quite interesting, I think, because when I talk with Michael usually talks about the recursion, but you never talk about the core recursion in the conversation, right? But Steve's first comment was this duality, and in that sense, it's already making sense to me. Yeah. Okay.
And so yeah, and there are again category theory sort of systematizes the various notions of recursion, which I think in languages I did a small lit review of this in the philosophy and language aspects of it. And the concept of recursion is not so well understood in language, but from a category theory perspective, it seems to be pretty straightforward. So again, it's not that the particular category theory construction is necessarily the answer, but for me, it provides a sort of a solid landmark as to how to relate what other people are talking about when they mean recursion versus what category theory is talking about.
And the thing that you said, and so Marco mentioned or brought up just a couple of minutes ago, is like this mentalizing as well, right?
Mm-hmm.
And you also mentioned like number numeration kind of ability is also part of this, which can be also uniformly described or explained by category theoretic perspective, right?
Yep. Yeah, that's another aspect. But the whole lot, and this gets to notion of structuralism, I suppose, is that there's no the sort of the prevalent view in cognitive science is there must be every sort of representation must sort of have some sort of essence to it, sort of like a set theory perspective, like number. What is essentially a number, you know? Whereas the category theory perspective, it doesn't look at the essential properties, but looks at the relationships between. So you have this so-called in category theory, there's the so-called number object. It's just like a graph that says all numbers have these properties. It really just encapsulates the basic properties of a number system in terms of its relationships between. And so I think it provides a different perspective from what cognitive scientists are more familiar with. You know, gets away from this notion of sort of essentialism, I suppose it's called, that these representations have. And in the end, I mean, ultimately, the cognitive system must be a relation to the world anyhow. So, again, it just seems natural to look at the relational or structural perspective.
Okay. So about this aspect, is there any question or comment? Yeah, Makiko?
So you mean in terms of number, do you mean like mathematics as well?
I mean the cognitive concept of number versus the mathematical concept of I mean, numbers could be built up recursively, of course, but
okay. Use case leaving, but yeah, let's continue.
Okay.
A bit, yeah.
Sorry, could you rephrase the question, Makiko?
Yeah, because so Norman Chomsky regarded recursion as the key factor that distinguish animal communications and human communications. So that we have language as we develop. So we can make any length of language that composed with like that phrase, for instance. And then you know, Raikov, he is insisting that the mathematics or like treating a number or like a number concept is cognitive science. He is Chomsky's he used to say, yeah. So I was wondering, what do you mean by number? So in terms of recursion, I was curious.
Oh, well, there are several different ways of viewing a number, but
it's like a counting or like the concept of number.
Oh, the concept of number. Oh, sorry. Okay, sorry. The point that from the category theory perspective, there is no essential privileged number. It's just whatever conforms to a particular structure that is called the number object. I think it's, I forget now the exact name of it, but it's just a small category that, so for example, it just gets around this problem of having to say, well, there is some sort of essential thing that is what. So if you ask the question, what is the number one? What is a number? And you might, how would you answer that? Well, one way would be to look at specific examples. But if you're trying to, it's not like trying to ask, well, what is an apple? Where you can look at specific properties or the things that make up the constituents of an apple. You can't really say that with, it's difficult to say that with a number. How would you define what a particular number was? Well, in the category theory perspective, you wouldn't look at the essential properties of a particular instance, but you look at how they relate to each other. And if their relationship is so isomorphic or satisfies this particular graphical structure, then say for all intents and purposes, it is a number. It is the concept of a number. So the numbers are built up recursively. So in that sense, it's similar to what Chomsky would say, I suppose, but has a slightly different flavor to it. You're not restricted to a particular way of doing it.
I understand. Yeah, thank you. Yeah, it's clear.
The only point I was trying to make is that there's just different perspective. Instead of looking at the internal, trying to define something by its internal constituents, the category theory approach would define it by external relations. And so the concept of a number, it seems difficult to define numbers by whatever their internal constituents are, because they don't seem to have any. So the natural alternative is to look at their relationships to other things, and that's the category theory perspective on number.
And that's also related to, or essentially the same as the Yoneda approach, right? In a sense.
Yeah. And so in this sense, I suppose you could think that category theory is a kind of structuralism. So, I think the idea is that the concept of a group, for example, is not a set of elements, but it's part of a collection of such objects with common relational properties.
Yeah. So in that sense, I think the category theory perspective can make the sort of the structuralism into more mathematical, or provide the method to what we want to do, or what Levi Strauss wanted to do with the structuralism, I think.
Yeah. So I think in some sort of ironic sense, the category theory is more precise, despite its abstract nature. It gives very precise definitions for what these things are. That's one of the reasons I like it. So if I'm in doubt about a concept, then I can go to the definition and get its implications, and then get a clearer picture as to what's going on.
So because you said precise, it's kind of interesting to share you with my kind of I gave a talk on this adjunction and its relation to consciousness research in the debate between the consciousness of Qualia and the report, right? So I will let you know about this, Masafumi and Makiko, but later by sharing the draft and so on. But we are now, three of us are writing a paper to say that Qualia itself or experience is quite precise, or like a refined, like real numbers, and then the report is kind of discretized or categorized and coarse like an integer, right? And then if you think about only object like a real number and the integer itself, then it's very difficult to compare between them. But if we introduce the relations, like larger than or equal or something like that, then we can define both real number with the larger or equal and the integer with the larger or equal, right? And then between those two, we can define this notion of adjunction as a sort of the going from very fine to coarse, but coarse back to fine. And then because of this precise notion of adjunction, we can say quite a bit about the real number from integer. And so from real number to integer is not that surprising, but from integer to real is quite interesting, right? Because many people, including actually in fact Kant, going back to really the philosophy of the 18th century, there are lots of philosophers saying that whenever the measurement is imprecise, we can't talk about something about that with the science. So he actually said that psychology will not become a science because the internal monitoring is never precise. But now given the current science deals with all these imprecise measurement, right? Like brain activity, EEG or fMRI is all imprecise, but still we can say something about it. And that this relationship between the exact thing and its approximation is a kind of the adjunction. And then, but the interesting thing about this in the current science is that after explaining this kind of concept in my talk, the first reaction came that okay, that's interesting, but to make this notion more applicable, do you want to make this discordance or displacement as precise as possible? And then I kind of agree that by making the functors or measurement more precise, we can arbitrarily make this discordance precise. But the more important thing is that to realize that even if things like Qualia 2 report becomes imprecise, we can say a lot about Qualia through the reports or through the examination of the integer. That's the kind of the precision that you are saying, right? So for some people, precision is really the discordance, but for other people, precision is the fact that we can say even about this structure from the coarse measurement is quite precise to me.
Yeah, so I think that the conceptual difference, and the adjunction highlights this quite nicely, is that the precision is with respect to the relations, not with respect to the objects. That's how to resolve the two different perspectives. So the bijection is between so on the technical side of the notion of adjunction, the bijection is between the Hom sets. So it's sort of locally precise, not the bijection is not between the sets of objects. And this is one of the reasons why I think you often hear the phrase adjunctions are everywhere. Right? The reason for that is that an adjunction is a kind of local isomorphism. Rephrasing what I just said before, so it's a bijection between the Hom sets, i.e. the relationships between pairs of objects. The reason why that's interesting is because you might think of, so the traditional way of, particularly for analogy research, is to think about isomorphism as a bijection or a graph isomorphism between the source and the domain. It's a kind of global isomorphism, but in mathematics, or the original motivation or the original realization of why adjunctions are so important is that that kind of global isomorphism is very rare, often not very interesting. So it's the isomorphism tends to be more localized, or put it another way, nature is sort of more curved rather than flat. I.e., if you have two curves, globally they're not the same, but where they touch, you can think of that local region as sort of the local precision or isomorphism. So that's how I would see those two different perspectives being resolved.
I see. Do you want to say something or fine? You are muted.
Yeah, very fine. And curved and flat is some kind of analogy with differential geometry or Einstein's general relativity. But also the same kind of analogy is related to the micro and macro duality, like Izumi Ojima always stressed that invisible micro system, like a quantum system, quantum field, and the visible macro system, the apparatus which measures the behavior of a quantum field or something, is has a very similar relationship, like a junction. The Izumi Ojima always stressed that. And I think that Steve's comment is also related to such a context also, and I am completely agree with Steve's view.
Yeah. All right. So it's been already passing over the hour. So maybe we can. Yeah, this has been already quite dense and probably very interesting. I don't know if I because you joined from middle, so if you wanted to ask any question, that's fine. But if you missed the first part, maybe it was difficult to catch up possibly.
Yeah, it was a bit difficult, but eventually I'll pick it up. Thanks.
Okay, great. Is there any further comments or questions, Masafumi or Makiko? Otherwise, maybe Steve, to wrap up, maybe you can also mention briefly what's your sort of the next plan of your major direction of the research or something, if you want to, other than Qualia structure.
No, there are lots of things I'd like to do.
Okay, lots of things.
But yeah, I think the continuing with the how should I say? I plan to continue with the category 3 approach to cognitive science. I think it has a lot to offer, a lot that has yet to be explored. There are many concepts that I think are potentially useful for the field, not just the ones that we've already mentioned. And also, particularly in the field of consciousness as well, I think that it's also another interesting application. It's not an area that I would have gotten into except for Nao's encouragement, and so thanks, Nao. I think having I'm not an expert. I'm not really deeply into the consciousness aspect, but I think as we've been working together, that the category 3 has quite a bit to offer there as well. I think there are a lot of deep questions that have remained unresolved in the field of cognitive science that category 3 has a lot to offer. It may not have the specific solution, but I think it offers paths around the current obstacles that could be in the long term could be quite good for the field. So yeah, I would encourage other people, other cognitive scientists, to get interested in the basic concepts of category theory. I think it's been, for me, it's been something I didn't really dream of would be useful. It's just because I come from a sort of a formal background in computer science and because I'm mathematics as well. I thought it was just interesting in its own right, but I didn't really expect it to have that much to say, because it's a bit counterintuitive as to why category theory would be useful. I mean, it's natural in computer science because the notions of object and morphism quite closely related to types and so forth. But particularly in psychology, it's, you know, it's such a empirically, it's such a difficult field to work with. You don't get the same sort of solid data that you might get in other fields. But at some level, yeah, it's been quite enlightening for me, at least personally. So yeah, I would encourage other people to. And more recently, other people are saying to you, I think a lot of people were looking at category theory applications to other fields, but beyond just the standard ones. So yeah. So yeah.
Yeah, that's great. That's a great concluding remarks. So I guess I'll stop the recording here, and then thank you. Okay. If there is nothing you wanted to say. Okay.
Thank you.
Thank you.